This video is a part of Experience Scaler for Free initiative. To get full content, please visit the link given in the description below.
Very quickly introducing what we're going to cover today, right? So today we're going to talk about sorting. And why is sorting important? I mean, sorting is essentially nothing but arranging data that you have in a particular order, right? For example, if I have a few numbers, I could say I want to arrange them in an increasing order. Or if I have people, let's say I want to arrange them in the decreasing order of their height or increasing order of their height, etc. The ordering, because you are able to order something, helps you in a lot of things. For example, sorting might then help you do binary search on that data if you want to look for something. Or if I give you queries around, hey, tell me how many numbers are bigger than a specific number. That also, I mean, if the array is sorted, you can just look for the index of the first element bigger, and then you know how many numbers are bigger, etc. So sorting helps in those contexts if it is ordered. In fact, most NoSQL DBs, they actually try to maintain data in a sorted form. Sorted set is what it is called, because it makes searching for data, looking for data, doing a bunch of analysis on data easier and easier, right? So today, we're going to, just to elaborate, we're not going to talk about searching. I'm going to talk more about sorting. Sorting is arranging data in a particular order, right? So for example, if let's say give you 5 numbers, I give you numbers, let's say 5, 10, 3, 2, and 8. These are numbers in no particular order, right? Now, if I say arrange these numbers in an increasing order, where the smallest number comes at the front of the list and so forth, that part is called sorting. So, if you sort this, then you'll have 2, 3, 5, 8, and 10. It's an arrangement of the given numbers so that they are in some particular form or order. As I said, like, the reason why it is important is because it helps you do a bunch of different kind of operations on the data fairly quickly if what you have is sorted. And I gave the example of NoSQL databases where they maintain data in sorted sets because it lets them do a bunch of different kind of queries in a sorted form. In fact, we will talk about some form of MapReduce when we go to system design modules. There also you'll see like a lot of things are generated in sorted forms because it allows for certain more operations to happen later on. Does everybody understand like what sorting is? So maybe like the way I would explain sorting is taking just like in binary search, I took the real world example of searching in a dictionary, what we normally do in real life. I'm again going to be taking the example, a real life example of what we might have done in our lives before, right? All of us went to school, and in school we were made to stand in increasing order of our heights. Now, let's take that example, which is I have a class full of people and I want to arrange them in increasing order of their height. Right now, assume they are standing in some random order. What are the different ways in which I can actually arrange them in increasing order of their height? And I'm going to take various sort of approaches I would have taken. And then I would sort of map it to what that approach is in real life. So approach one could be that I ask everybody to come one by one. And let's say if I have a few people already standing in the line, let's say I have few people that I've already arranged in the line. And let's say there is this new guy with this height that comes. In fact, it is better to imagine, maybe I can write the height of each of those individuals. Let me just write the height. So imagine I had somebody with height 1, 5, 12, and 27 already in the line. Somebody with height 7 comes. One thing which I can do is I can find the right position for this person, which is between 5 and 12. And I insert 7 there, which means then I'll have 1, 5, 7 here. And then 12 and 27, I'll push one space back. Right? So 12 comes here, 27 comes here, right? And then as people keep coming, let's say there is a person called 32. I'll figure out where 32 should lie here. I'll figure out 32 should come here. I'll insert 32 here. Everything up after 32 would be pushed one space back to make space for 32. Here there is nothing. This is called insertion sort. This technique where I get numbers. I figure out what is the right location for them. I can do that through binary search, or I can do that through a linear scan. Either is fine. Once I find out what their location should be, I shift all of the other numbers one space to their right, and then insert this new number at the new location. Now, that is called insertion sort. If I have to write the approach for this or the steps for this, basically assume that I am maintaining my sorted array in, let's say, sorted array list. That's a sorted list, which is initially empty. And imagine I keep getting a few numbers, right? What I do is I start from the end of this list. For example, here, if I had 1, 5, 12, and 27, and I wanted to insert 7, I'll start from the end. Is 7 already bigger than 27? It is not. So what I would do is I'll shift 27 one space to its right. So imagine this was the array. I have one space left here, so I'll shift 27 to its right. So 27 comes here. Then I go and again check 12. Is 7 bigger than 12? No, it is not. So I'll shift 12 to one space to its right. 12 comes here. Then I check the next number, which is 5. Is 7 bigger than 5? Yes. That means this is the location of 7, and I insert it here. I keep doing this with every new number that I encounter, and that makes for what is known as insertion sort. What is the best case complexity here? Best case time complexity here. And what is worst case time complexity here? Best case for sorting. Order 1 would be the time complexity of inserting a new element, best case, right? Because you start with 7, you'll find that, let's say the new element that we are inserting in this new array, let's say that is 32. Best case is I look at the first element and I find that 32 is bigger than that, and therefore 32 just gets inserted here. It is for the addition of the last, like the new element. Order 1 is the best thing that you can do, but you'll have to add n such elements. So therefore, if you do order 1 for n elements, you'll end up with order n best case complexity. So in the best case, insertion sort will take order n time. What is the worst case? When do we get the worst case? What is the worst case, and in what kind of data would we get worst case? If the array was reverse sorted, which means if, let's say, I was giving you numbers, I first give you number 5, you insert 5. Then I give you 4. You insert 4 here, right? Because you'll have to shift 5 1. Then I give you 3. You'll figure out that actually 3 is smaller, so you'll shift 5 here, and you'll shift 4 here, and then 3 comes here. Then I give you 2. You'll again shift 5 here, you'll shift 4 here, you'll shift 3 here, and then 2 will come here. And then again, you'll do one more shift and to get 1 in if 1 is the next number, right? This ends up taking, for the first number, you take 1 step. For the second number, you take 2 steps. For the third number, you take 3. And for the fourth number, 4 and 5 and 6 and so forth. So this becomes almost order of n square. So worst case, this might take order of n square when the numbers are sorted in decreasing order. A very interesting question, which is, does the time complexity affect if we take linked list? There are two parts here, right? Like one is, there are two things that we're looking for. One is, what is the right index where this new number should go? And the second is shifting greater numbers to make space. One place right. So your linked list will save you on this time. So this time will become 0. However, finding this 1 in a linked list, because you can't really jump to a random location, you'll have to do a linear scan to figure out where the number should occur. Right? So that might still end up taking order of n square, because searching for the right index, the step number 1, that might end up taking order n. You can't apply binary search in linked list because you can't just jump to a random location in the linked list. Right now, the way I explained insertion sort was that you were getting a stream of numbers and then you're sort of sorting it by putting them in the right location. Now, whatever I said, that can also be applied to an existing array as well. Let me explain. Right now, the way I detailed insertion sort is by saying that, you know what, like 5, I am getting 5, then I'm getting 4, then I'm getting 3, then 2, then 1. Imagine I was already given an array, right? So imagine I had the array as, let's say 5, 8, 3, 2, 18, hypothetically, right? And I asked you to sort this array in place without using extra memory. I do not want to use any extra memory. Can you sort this array without using extra memory? Insertion sort. So I don't again have the flexibility of creating a new array. I am doing this in place. How do we do that in place? Even when you're doing in place, imagine I start from 5, right? So first I'll start with 5. I'll say I only have to sort this. 5 is the new number that I've gotten, right? So I have one place, 5 is the new number I've gotten. Obviously, it will go at this position. So 5 comes here. Then I go to the second number. And I say, let's put this in a temporary variable. Temp is equal to 8. Now, 8 is the new number I'm trying to insert in the first two locations, right? So first I'll compare with 5. Is 8 already bigger than 5? Yes, it is. So it will come here. Then I look at sorting the first three numbers. I pick 3. So I delete 3 from here, imagine. And it is, this 3 is the new number to be inserted. So first I check with 8. Is 3 bigger than 8? No, it is not. So 8 will come here. Is 3 bigger than 5? No, it is not. So 5 will come here. And then 3 gets inserted here. So now if you look, I mean, by now I have the first 3 numbers sorted. Now I'll take this number 2, which is I'm trying to sort the first 4 numbers. I'll take the new number 2 and imagine that 2 is the new number that I was getting. So I put this in a temporary variable. I'll do the same comparison. Is 8? No. So 8 comes here. Is 2 bigger than 5? No. So 5 comes here. Is 2 bigger than 3? No. So 3 comes here. And then 2 comes here. And then finally 18 is bigger than 8. So 18 will directly come here. Does that make sense? So same approach. All I'm doing is I'm saving on the additional space if an array is given to me already. The worst case time complexity is still the same. Nothing has changed in the approach. I'm just using the same space that was there in the array instead of creating a new array. Okay, so if we apply binary search for position, it will contain more computations, right? Finding plus swapping. Yes. If you do apply binary search, you'll first take log n time to find the right location. And then in worst case, order n extra time to create the space. I mean, right shifting all of the elements to create space for this other element, right? So it will end up taking n plus log n every single step instead of just n every single step. So this log n is additional. Overall time complexity will still remain n square because you'll do this n times. So instead of n into n, you'll get n into n plus log n, which is basically n square plus n log n, which is still order of n square. But why do that? I mean, why do this additional operation? Why not just start from the end? You have to shift the bigger elements one step to the right anyway. So just start from the end, shift the elements to the right, and then like fit the element wherever you find the first place. All right, everything clear till now? So that is one way in which you would sort, let's say, your classmates, right?
If you like the video, please do not forget to like, comment and share this video with all your friends. Also, subscribe to our channel to get notified about the new upcoming videos.